Today we shall discuss about the linear expansion. Now expansion means you have a rod of length L, and if you supply the heat, okay, then its temperature is increased by delta T, then there is change in length by delta L, okay. Initial length is L. Now this delta L is found to be directly proportional to the initial length and change in temperature. If you combine them, then delta L is proportional to L into delta T. Okay. So delta L upon L is proportional to delta T. Hence, the fractional change, that is delta L upon L, is directly proportional to the change in temperature. Now if you remove this proportionality, okay, then we put one constant, that is alpha L, where alpha L is the coefficient of linear expansion. So we can say delta L is equal to alpha L delta T, okay. If say delta L is L2 minus L1, that is final length minus initial length, and delta T is T2 minus T1, that is final temperature minus initial temperature. Then instead of this delta L, you can write L2 minus L1, and instead of this delta T, you can write T2 minus T1. And if you simplify, then you will get L2, that is final length, is equal to L1 plus alpha L, L1 T2 minus T1. If you take L1 as common, then L2 is equal to L1 1 plus alpha L T2 minus T1 you will get. If you write alpha L as alpha and L1 as L, then final length L2 is equal to L 1 plus alpha T2 minus T1. This is the table which gives you the value of alpha for different material, okay. Now we have anomalous expansion of water is blessing for living organism in water, okay. Now see, anomalous expansion of water we are going to discuss. Thermal expansion of water is non-uniform with temperature for water, that is anomalous expansion. Now it contracts on heating between 0 degrees Celsius and 4 degrees Celsius. The volume of given amount of water decreases as it is cooled from room temperature until its temperature reaches 4 degrees Celsius. So until 4 degrees Celsius, its volume decreases. Okay, volume of water decreases up to 4 degrees Celsius. Below 4 degrees Celsius, the volume increases and therefore the density decreases. This means that water has maximum density at 4 degrees Celsius, because up to 4 degrees Celsius its volume decreases. So its density is maximum at 4 degrees Celsius. This is the graph of density versus the temperature, that is between 0 degrees Celsius to 10 degrees Celsius. Its density increases, okay. At about 4 degrees Celsius it becomes maximum and then it falls, okay. So this is the anomalous expansion. This property has an important environmental effect. Bodies of water such as lake and ponds freeze at the top first. On the top it freezes. Inside the water remains at 4 degrees Celsius temperature. Okay, water near the surface loses energy to the atmosphere and becomes denser and sinks the warmer, okay. Less dense water near the bottom rises. However, once the colder water on the top reaches temperature below 4 degrees Celsius, first of all what happens, the water from the surface goes below and the water which is at bottom comes top, or we can say comes at the surface. This process goes on till the temperature of whole water body becomes 4 degrees Celsius. Now that temperature of whole water body is now 4 degrees Celsius. Now what will happen? The water from the top will not go to the bottom, and from water from the below, that is bottom, will not go to the surface. Now what will happen? The surface water will start becoming ice, okay, or its temperature reduces and becomes 0, okay, so that freezes, okay. If water did not have this property, lakes and ponds would freeze from the bottom to the top, okay, and that may destroy the animal and plant life, okay. So this property of anomalous expansion is beneficial for the living organism, okay, we can say. Now we shall find out the coefficient of volume expansion from ideal gas equation. Now we have the ideal gas equation, PV is equal to mu RT, where P is pressure, V is volume, mu is number of mole, R is gas constant, and T is absolute temperature. Now at constant pressure, P delta V is equal to mu R delta T. If you change the temperature, volume changes, okay, that volume change is delta V and change in temperature is delta T. Now if you take the ratio of 1 and 2, then PV upon P delta V, okay, will be equal to mu R T upon mu R delta T. So P will be cancelled out. Now taking inverse, we have delta V upon V is equal to, this mu R will be cancelled out, delta T upon T. So this equation you are getting, okay. Now delta V upon V delta T, that is nothing but coefficient of volume expansion. So what is done? Delta T is taken in the denominator. So we have delta V upon V delta T is equal to 1 upon T, and this is the coefficient of volume expansion. So alpha V is equal to 1 upon T, okay. For ideal gas, alpha V is equal to 3.710 to the power minus 3 Kelvin inverse at 0 degree Celsius, which is greater than solid and liquid, okay. Now what will happen if the rod is tied with fixed support rigidly at both ends and temperature is increased? Say for example, a rod is tied rigidly at both the ends, and if you increase the temperature, what will happen? Now say for example you have a steel rod, okay, which is the length of the steel rod we consider as 5 meter, cross sectional area we consider as 40 centimeter square. Thermal expansion is prevented by decrease of 10 degrees Celsius in temperature, okay. Now coefficient of linear expansion for the steel is known, okay. Now there will be a slight change in length due to temperature change, okay. So it is a compressive strain, so delta L upon L, okay, and as you know delta L is alpha L del alpha, that is coefficient of linear expansion alpha L into delta T. So delta L upon L you can find, okay, that is alpha of steel into delta T, and 10 degrees Celsius temperature we have, or rather 10 degrees Celsius temperature difference we are taking. So alpha of steel into 10, so that delta L upon L will be 1.2 into 10 raised to minus 4. Now Young's modulus is compressive stress upon strain. It is stress upon strain, okay. So we can find delta F upon A, which is nothing but compressive stress. So Y is into compressive strain will give you compressive stress. So Y into delta L upon L that we have calculated. Just we have to place these values and you will get the answer for delta F. If you multiply this A, then delta F will be equal to, will get Young modulus delta L upon L into A, and A is given to us area of cross section 40 into 10 raised to minus 4. Just multiply, you will get 10 raised to 5 Newton change in the force. Thus, by this value of the force with two rigid supports, track can be bended. Okay, track will be bent. Okay. Now we talk about the heat capacity of substance. Okay, we will write its equation also. Now there is one activity given to us. Okay, in the first step we have to heat a given quantity of water to raise its temperature by say 20 degrees Celsius. So you are raising a temperature of say 100 gram water you are having, and you are increasing the temperature from the initial temperature by 20 degrees Celsius, and we note down the time, how much time we have to give the heat to this given quantity of water to rise its temperature by 20 degrees Celsius. Again take same amount of water and raise the temperature by 40 degrees Celsius. Using the same source of heat, what will happen? Time taken, we have to again note down, and we will find that the time taken will be double, because now you are increasing it by 40 degrees Celsius. Okay. In the second step, now suppose you take double the amount of water. Now you are doubling the amount of water. Say initially you have taken 100 gram, now you are taking 200 gram. So you are doubling the amount of water. Okay. Now again you are increasing the temperature by 20 degrees Celsius. Okay. You will find the time taken is again twice the required in the first step. Okay. You will change the temperature by 20 degrees Celsius only. Okay. And the amount of water is double, so naturally the time will be double. Okay. Now in the third step, third activity, in place of water, now heat the same quantity of some oil with say mustard oil and raise its temperature by 28 degrees Celsius. So 100 gram mustard oil you have taken, changing its temperature by 20 degrees Celsius. Note down the time. Okay, with the help of the stopwatch, we'll find that time taken will be shorter. Okay. Therefore, the quantity of heat required for oil would be less than the quantity of heat required to raise the same amount of temperature that of water. Okay. This observation show that the quantity of heat required to warm a given substance depend on its mass, the change in temperature, and the nature of the substance. The change in temperature of substance when a given quantity of heat is absorbed or rejected by it is a characteristic of a particular substance, and it is called the heat capacity of the substance. Okay, when you are supplying the heat, whether it is rejected or whether it is absorbed, it is the nature of the substance. Okay, so we can say that heat capacity is the ratio of heat given to substance and corresponding change in temperature, that is delta Q by delta T. The delta Q is the amount of heat supplied to the substance to change its temperature from T to T plus delta T. Okay. Value of heat capacity depends on type of material and the mass. Okay, this is very important. Type of material and mass, on these factors the value of heat capacity depends. Heat capacity of substance of same material but different mass can be different, and unit of this heat capacity is joule per Kelvin or calorie per Kelvin. Try to watch this video 2-3 times and understand it. Okay, thank you very much.